Imagine a main canal, a continuous, gravity-fed open channel where thousands of cubic meters of water flow swiftly through a wide earthen trench. The central challenge in irrigation engineering is taking this massive, unmanaged flow and accurately splitting a portion of it off into a smaller secondary network, known as a distributary. Digging a side channel without a gate results in failure. An unmanaged ditch cannot capture a reliable volume or maintain the pressure required to push water across long distances. Downstream, there is a cultivable command area, thousands of hectares of agricultural land that rely entirely on a highly predictable, mathematically exact flow of water to survive. Agricultural success dictates that the water levels in the secondary network cannot be left to natural seasonal fluctuations in the parent river. The mandate is clear. Engineers must physically force water to leave the main canal at a precise, calculated rate, and they must do it without risking a structural washout. A canal junction operates as a highly active, tightly controlled mathematical metering point. Before any concrete is poured, the required volumetric flow rate must be determined, and that number is derived entirely from the biological needs of the crops. Engineers calculate this demand using two specific metrics: duty, which is the area of land that can be irrigated by 1 cubic meter of water per second, and delta, the total depth of water the crop requires over its lifespan. Looking at this calculation sheet, command area acreage is combined with crop duty to establish baseline agricultural discharge for different growing seasons. Accounting for a 20% transmission loss allowance, we arrive at the final required discharge, exactly 39.06 cumex. Firm. That specific calculated volume must be maintained and delivered into the distributary channel, regardless of how low the water level in the parent canal drops during a dry season. With the theoretical agronomic demand established, the problem shifts to the physical infrastructure required to achieve it. Mathematical crop requirements are useless on paper without the heavy concrete and steel architecture designed to enforce them in the field. The first piece of hardware required at the junction is called the cross regulator. This structure is positioned spanning the main channel, situated directly downstream of the offtake point. Mechanically, it operates by lowering massive vertical lift gates directly into the water path to physically restrict the downstream flow of the parent canal. By blocking the path, these gates artificially force the upstream water level to pool and rise to a designed full supply level. Elevating this water column creates hydraulic head, the distinct driving pressure that pushes horizontally toward the mouth of the offtake channel. Without this controlled restriction, during periods of low seasonal flow, the water would simply drift straight down the main canal, bypassing the offtake entirely. The cross-regulator generates the power and pressure needed to push water sideways, but it does not meter the actual volume entering the distributary. Generating this upstream hydraulic head is simply the absolute prerequisite for commanding any secondary irrigation network. To manage the volume, we need a companion structure, the distributary head regulator, built exactly across the mouth of the offtake channel. Its primary function is to act as the precise volumetric metering device for the entire downstream agricultural system. Engineers calibrate these gates in tandem with the full supply level maintained by the cross-regulator to allow a highly specific volume through. Under normal operation, it meters out that exact calculated discharge volume of 39.06 cumex, smoothly feeding the distributary network. However, the structure has a secondary operational function. It must be capable of shutting off flow entirely, allowing for downstream channel maintenance or sealing the system during off-seasons. This introduces an extreme physical condition. The head regulator gates drop fully closed, but the parent canal remains running at full supply level. This closed state creates a massive static head difference. You have tons of pressurized water pushing against the upstream side of the gates, and a completely empty dry channel on the downstream side. While the steel gates successfully hold back the surface water, they simultaneously create a severe pressure imbalance, threatening to destroy the foundation they stand on. To understand the threat, we have to shift our focus from the visible surface water down into the invisible, porous soil foundation beneath the concrete. That static head difference means immense water pressure upstream is aggressively pushing against a dry, low-pressure void downstream. Finding its path blocked by the steel gates above, the pressurized water seeks an alternate route, seeping directly underneath the concrete substructure of the head regulator. This flow creates steep hydraulic gradients through the earth, introducing a catastrophic structural risk known as piping. As the seeping water finally reaches the dry side downstream, it accelerates upward to exit the soil. If this exit velocity is too high, it washes out the foundation particles, effectively hollowing out the earth until the massive concrete structure above collapses into the sinkhole. To neutralize this threat, engineers use Kozlow's theory of independent variables, a mathematical framework used to calculate and manipulate subsurface pressures. The operational survival of the visible surface gates depends entirely on successfully managing this invisible subsurface exit gradient. Kozlow's equations provide the precise geometric solutions needed to prevent piping failures and secure the foundation. Looking at the engineering parameters of this test case for a head regulator, we see a system designed to handle a 1.5-meter static head difference. The primary defense mechanism is casting a massive 13-meter-long impervious concrete floor beneath the regulator gates. This floor artificially extends the seepage path length, forcing the water to travel further horizontally and bleeding off hydraulic energy through friction along the way. This is augmented by a 2.5-meter-deep upstream cutoff wall driven into the soil, which immediately drops the initial uplift pressure by forcing the seepage to dive under it. Finally, a 2.0-meter-deep downstream cutoff wall is placed exactly at the critical exit point, forcing the flow lines to travel deep underground before they can turn upward to escape. In the mathematical solution, this final downstream barrier ensures the exit gradient drops to 0.123, pulling upward velocity below the critical failure threshold. The massive concrete geometry buried deeply beneath the regulator is the direct physical manifestation of these fluid mechanics equations. Pulling back, we observe the completed canal bifurcation complex operating smoothly as a single unified system. The cross-regulator reliably commands the required depth and hydraulic head in the main channel. The head regulator translates that head into a perfectly metered discharge for the downstream crops. And the unseen, deep-set foundation continually protects the entire multi-ton apparatus from catastrophic uplift and piping beneath the soil. Irrigation engineering sustains agriculture by establishing a delicate, permanent equilibrium between these immense physical forces.